right, so we're going to talk more about trees today, algorithms, and we'll look at some code and things like that. Any questions before we get started on either trees or midterm or PA3 or anything? Yeah.
If we get snowed in tomorrow, in terms of the midterm, would you just have like a second?
Yeah, so if it does snow and people can't make it, right, I'll put together a second test and we'll figure out a time next week to give it.
And it
So,
would be like the same topics covered on.
yeah. Hopefully like comparable difficulty. But if that happens and if people make it in tomorrow, I'm going to ask people not to talk to anybody about the midterm until after everybody's taken it. And I'll just have everybody on their honor. I'll give you a different exam, but it's going to be kind of the same type of stuff, so I don't want people to think there's advantages there. So, but yeah, if you're in doubt, you know, play it safe. It's not a big deal doing another exam. All right, well, let's look at trees some more. I'm just going crazy here, don't worry about it. So there's a big old tree, it's got lots of stuff in it. And we want to add some nodes to this tree, so let's think about an insert function. And somebody give me a number between 1 and 100 that's not already in the tree.
77.
77, nice number. Let's insert 77 into this tree. So what do? We begin at the root. And 77 is bigger than 40, so if we're going to insert it into this tree, it's got to go somewhere on the right. Agreed? So we move to the right, and the root of this tree is 60. 77 is bigger than 60, so it's got to go somewhere in the right subtree. So we move to this smaller tree, and the root is 80. 77 is smaller, so it's got to go somewhere in the left subtree. There's nothing on the left. There's no tree on the left of 80, so we're going to put our 77 right there. All right, so give me another number. 2. All right, smaller than 40, go to the left. Smaller than 20, go to the left. Smaller than 15, go to the left. Nothing there. That's where the 2 goes. So it's a really simple algorithm. Start at the root and just move your way down, going left and right until you get to a node where there's nothing on the side that you would like to go, and that's where you put your new number. So insert 34. Smaller, bigger, bigger, smaller, bigger, nothing there, 34. So that's not a bad algorithm to write a loop for. We can do exactly what we just did on paper. So let's make an insert. And we'll insert root comma num. And we'll say if num is bigger than root data. So if the number we're inserting is bigger, what do we want to do? We want to move down to the node on the right. So we're just going to say root equals root right. And we're going to go back up to the top. If our number is less than the root data, And I'm going to assume we're not inserting something that's already in the tree. So this if isn't really necessary, because if it's not bigger than the root, it's got to be less than. So we'll just change the root to the left subtree, and we'll go back up to the top.
What if it's equal to?
We're going to assume we're not inserting something that's already in the tree, just to make it easier.
So we perform the search before we insert.
So you perform the search first, yeah, or you trust your user. We could check to see if it's equal, and if it is, we could just halt and catch fire or something. Well, this is great for moving down the tree, but what happened when we were trying to insert 77? We'd set our root to be here. 77 is bigger, we'd set the root to be here. 77 is smaller, we would set the root to be the left child, which is a null, and as soon as our root is null, this is going to segfault. So we also need to do a check in here, which could look like this. Before we move to the right, let's do the following. If root right equals null, set root right equal to our new node, and we're done. So when you decide you're smaller than a node, before you move down to the left, check to see if there's actually anything there. If there's nothing there, just go ahead and set that child to be equal to your new node, right? That's adding your node right there. And the same thing on the left. Before we move to the left, if root left equals null, set it equal to the new node and return. So this will successfully take a tree, you pass it the root, and it'll march down, it'll keep reassigning the root until it gets to a point where, say you're inserting 89, root will be right here, it'll say there's nothing to the right, so we'll set the right child of this node to be our new node. And that would tack an 89 on there. So you need to create a new node, right? Call malloc, set the data equal to num, set left and right to null. There's one special case in here, though, that we're missing. And that's what if you try to insert into a tree that's null to begin with. So if we don't have any nodes in our tree, like we just started our program, and we say insert the number 10 into this empty tree, well, as soon as we try to do root arrow data, we're going to segfault, because root's null. So we really need to do something up front. And this is where things get a little bit tricky, but not too bad. So, two possibilities. Possibility one, the tree is not null. So maybe our tree looks like that. And in that case, our insert algorithm works perfectly. But case 2, T is null, and our tree is just nothing. There's no nodes. Right? Remember, there's no sentinel nodes here with trees. So an empty tree is null. Right? It's a special case, and we're using the fact that our root is null as a flag base, basically to say there's no nodes in the tree. And if we pass null to this, we're going to segfault when we try to look at the data at the root. So what we'd like to do is, we can actually come back here, we'd like to do a special check first and say if the root is null, change root to be whatever the new node is. So if we say insert 20, t should look like this now in the first case. But in the second case, t should look like a single node. As long as there's stuff in the tree to begin with, the root never changes. But there's one edge case, which is if the tree is empty to begin with, after we call insert, the tree is going to change from being null to being the address of some root node. And this is a problem because we're passing the root by value. Everything's passed by value. It's a pointer to a struct node. It's an address in memory. But if this value is null when we call insert, it's going to be null when we get back. So how are we going to change the root to be that new node?
Give it a pointer to the pointer.
We could give it a pointer to a pointer. That's too many stars. But that would work. We're going to do something a little different, though. We're going to make this function actually return a struct node star. So here's the whole prototype for insert. So struct node star insert. It's going to take an argument, which is a struct node star. That's the root right now. And it's going to take some kind of data we want to add, like an integer. And in our main program, we're going to have some variable that represents our tree. Let me just call it root. Let me call it my root. And we're going to initialize it to null. That means we have an empty tree. When we want to insert into this tree, we're going to have to do the following. My root equals insert my root comma num. And this is the price of not having a sentinel. So when we call insert, we definitely have to pass it the root of the tree and the thing we're inserting, but we also have to take the return value from that insert function and reassign my root to that new value. And there's only one time when this makes any difference, and that's when we're passing null, and we're going to get back a value that's not null. This will make my root point to the root of the new tree. But there could be other times when this is useful. For example, if your tree looks like this, and here's the root, and you say insert 30, well, eventually, instead of coming back with a tree that looks like this, we're going to want to come back with a tree that looks like this. Why? Because this is wider and fluffier than that. It's more balanced. It's going to perform better. And so in this case, insert is given a root that contains a 10, but we'd want to return a root that contains this 20. So in general, when we work with trees, most of our functions, insert, delete in particular, are going to take a root, but they're also going to return a root. And whenever we call, we're going to say root equals insert root. Is that clear? It'll be more clear when you're actually coding these things up. All right, so this isn't too bad, right? We gotta create a new node. We've got to see if the root's null, and if it is, make a new node and return that. Otherwise, we have a loop where we say move to the right or move to the left, and inside each of those, we see if the way that we would like to move is null, and if it is, we create a new node and tack it on to the right side or the left side. And that's not too bad to code. It's a chunk of code, but it's too much work for a Thursday. So let's look at the lazy approach. So let's insert I don't know, Do we have a 25? Let's insert 25. And I don't feel like having all those variables and following down and making while loops and all that sort of stuff. I want to be really lazy about this. So here's what I'm going to do. I'm going to look at 25. I'm going to compare it to my root node. 25 is smaller. So I know my 25 is going to go somewhere in this tree. Agreed? So I'm going to take this tree, I'm going to hand it to a friend, and I'm going to say, can you insert 25 into this for me?
He said no.
They say no. Get a new computer. They'll say sure. They'll take this tree, they'll do whatever they have to do to put a 25 into it. They'll hand me back a new tree. I'm going to replace this with the tree they give me back, and I'm done. And I didn't really have to do any work. I left it all for my friend. So if I want to insert a number, I'm going to compare it to the root. If it's smaller or larger, I'm going to take either the left subtree or the right subtree, and I'm going to get somebody else to insert my number into that. I'm going to take the resulting tree and just replace my left or right subtree with that new tree, and we're finished. And you know the usual drill, right? How's my friend going to insert 25 into this? They're going to say it's bigger than 20, so they're going to look at this subtree, hand that to a friend, and say, can you put 25 in there? The tree they get back, they replace this with that, and they hand the whole tree back to me, and I replace the left subtree with that, and we're done. And this is trivial to code, as most good recursion is. So let's look at this. Struct node insert. There's an edge case here. It's the same edge case as before. What's the one case where I can't hand a subtree to a friend to do the insert?
A null.
Yeah, if I don't have any subtrees, I can't do that. Right, so our edge case is going to be if root equals null. Then I got to actually create a node, but it's easy to insert a node into an empty tree. The result is just a tree whose root is that one node we're trying to insert. So I can say root equals malloc, root data equals our number, set the left and right children to be null, and return the root. So that's the one case where we actually have to do some work. If there's nothing in the tree, we'll make a new node, set the data, the left and the right appropriately, and just return that root. Otherwise, we do the following. If our number is less than the root data, then root left equals insert root left comma num, and return the root. I'll throw some curly brackets on. Otherwise, the number must be bigger than the root data. So we'll do the same thing, but we'll do it on the right. We'll say root right equals insert. Pass it the right subtree. Let insert do the heavy lifting of inserting the number into that. Set the root right equal to that new tree and return the root. And there's your whole insert function. So it's classic recursion. It's just deferring to ourselves, because we're our own friend. And the only time we actually do work is when the tree is empty and we just create a node and return the address of that node. And this actually works. And it's a whole lot easier than the iterative version where you have to loop and move down the tree. And the amount of recursion isn't bad. Each time that you call insert, you're working on either the left or right subtree below the root, which means the height of that tree is one less than the height of the original tree. Or could be significantly less. But it's at least one less because we're removing the root from that tree. So if the height of the original tree is k, at most we're going to call ourselves k times, at which point we'll be down to a null child, and that's where we'll insert. So it's pretty efficient, doesn't chew up a lot of memory, and a whole lot easier to write, but a whole lot more difficult to debug. So fortunately, most of these recursive things either work or they blow up gloriously in most cases. So debugging them, something like this, right? If you get something wrong, it's going to be pretty obvious that there's a problem. But trying to debug a general recursive routine can be pretty nightmarish because you got to keep track of what's called a call frame. Basically, who was I called from? Where am I in this list of things that were called? And they're all the same function. So that's its own challenges. All right, so questions on that? We'll be digging more into these next week, and when we start talking PA4, we'll go through some more code. But just giving a high-level overview of tree operations for now. All right, so let's talk a little about balance. So here's a perfectly fine binary search tree. Contains 1, 2, and 3. Everything to the right's bigger than the root. Here's another binary search tree that has the same numbers in it. And here's a third that has the same numbers in it. They all work as BSTs. They all have the same 3 numbers, 1, 2, 3, but they look different from each other, right? And their behavior in terms of performance is slightly different. If I'm searching this tree for a number, at most I have to do 1, 2 comparisons. With these, at most I have to do 1, 2, 3 comparisons. So lower performance potentially. A more extreme case, again, the same 7 pieces of data, 2 different forms of the tree. Searching this tree at most 1, 2, 3 operations. Searching this tree 1, 2, 3, 4, 5, 6, 7 operations. Right, and again, this is just a linked list. We know linked lists are order n. This is a kind of classic binary tree, and this is going to be order log n. Log n is better than n. So we'd like to somehow know that the trees we're working with are more like this and less like that. And so there's a concept called balance, and balance basically says how much does the tree look like this versus that. The goal of this is basically to minimize the height of the tree, to make sure that the depth of each node is as small as possible, roughly speaking. So the problem here is that this node is very deep, so the number of steps it takes to reach it is very high. If we keep all the trees sort of shallow, all the nodes sort of shallow, then we minimize the number of steps it takes to get anywhere. And visually, a balanced tree is going to be shorter and wider, and it's going to be more kind of evenly filled in. So this is not a balanced tree. Even though this part up here is nice and fluffy, we've got this straggling thing over here, right? And this is going to be lopsided on the right. It's a technical term. So there's a notion of balance, and the first thing we want to do is be able to measure the balance of a tree to tell whether or not a tree is balanced. And what we're going to do eventually is that as we're inserting things into a tree, we're constantly going to check to see if it's balanced. And if we have a balanced tree and we insert one node and it becomes unbalanced, that's easy to correct. If you start with something like this, it's very hard to balance that. You got to do a lot of work. But if we had something that was nicely balanced and we put in one node and now it's lopsided, it's pretty easy to correct. It's a matter of 1 or 2 operations, which are called rotations, and it'll bring it back into balance. So we want to know if a tree is balanced or not, so let me give you a definition. And the definition is recursive. So a tree T is balanced if, okay, 3 things have to be true. First thing, the left and right subtrees have to have almost the same height. If one subtree is much taller than the other subtree, right there we can say it's not balanced. So the way we write this mathematically, absolute value of the height of T left minus the height of T right. They don't have to be exactly the same, but they have to be within 1 of each other. So one tree could be slightly higher than the other, one subtree. That's fine, as long as the difference is no more than 1. And we also need the left subtree to be balanced and the right subtree has to be balanced. So a tree T will be balanced if its left and right subtrees are almost the same height and the left and right subtrees are both balanced themselves. Or T is null. So there's 2 ways a tree can be balanced. It could be completely empty, and that's going to be balanced by definition, or it can satisfy these 3 conditions on top. Left and right subtrees close in height, left and right subtrees balanced. And how do you apply this test recursively? Right? If you're lucky and the tree is empty, you can just say, yeah, it's balanced. But if not, you got to do some work. So let's try this. We'll talk more about this later, but let's just try this. So is this a balanced tree? We would hope so, right? T is null. So we'd hope this would be balanced, so let's suppose this is T. Well, left and right subtrees, there's the left subtree, there's the right subtree. So what's the height of a tree that has just a root? Remember?
0.
It's actually 0. But whatever it was, we know these 2 trees have the same height, right? So that's fine. So the question comes down to, is a tree with a single node balanced? Well, the left and right subtrees are null,
The difference is less than 1, so
and the difference is less than 1, right? Null trees both have a height of -1. So condition A is satisfied. And is the left subtree balanced? Well, yeah, if a tree is null, it's balanced. And the right subtree is balanced. So this is balanced. So this is balanced, and this is balanced, and the height of the left and right subtrees differ by 0. So this original tree T is balanced. So a single node is balanced. A thing with 3 nodes like this is balanced. What about a tree that looks like this?
Not bad.
I see both answers. So the left subtree is a node containing a root. The right subtree is null. So the height of this tree is 0. The height of the null tree is -1. That differs by 1. So condition A is satisfied. We already saw that a tree containing just a single node is balanced, and the right subtree is null, and a null tree is balanced. So this turns out to be balanced also. But this will not be. And the reason it won't be is the left subtree has a height of 1, and the right subtree is null that has a height of -1, and the difference is 2. So right there we can say not balanced. But if we do this, balanced or not? That'll turn out to be balanced because left subtree has a height of 1, right subtree has a height of 1, same height, so condition A is satisfied. And we saw up here that a tree containing 2 nodes like this is balanced, and we could also do the analysis on that, and that'll be balanced. So this is actually balanced, which doesn't necessarily feel right, but according to the definition it is. But as soon as we hang another node somewhere, it'll stop being balanced. Okay, so that's our definition. Let's just sketch some code. So integer balance root. So if the root is null, return 1. So I'm assuming we have a height function and an absolute value function. So if the height of the left minus the height of the right, absolute value of the difference is less than or equal to 1, and root left is balanced, and root right is balanced, return 1. Otherwise, return 0. And there's your whole balance function. So a lot of work being done in here, but very little code. And remember how we find the height of a tree. We find the height of the left and right subtrees. We find the largest of those 2 numbers, and we add 1 to it. And if the tree is null, we just return -1. So that's the recursive function itself. So this is the definition. This is what you need to remember, right, for future tests, not tomorrow. But if you know this, right, the code is really a direct rendering of this definition. I checked to see if the root was null before I tried using root left, right? So put t as null up here before you start using things that t points to. But, is t left balanced? Well, I called balanced root left. And a lot of times with these recursive functions, the code will very, very closely mimic the algorithm itself. So you want to remember the algorithm, not the code. If you know the algorithm and you know how to write recursion, you can write the recursive code in your sleep and weird people out. All right, well, we got 10 minutes. We got 15 minutes. Let's tackle deletion. Say again? All right, there's a tree. I changed your root up on you. The root's 60 now. And we want to delete a number from here. Suppose we want to delete the 23. Okay, what's the lazy approach to this? Compare 23 to the root. It's smaller. Take the left subtree, give it to a friend, say delete 23 please. They give me back a new tree, I replace this with that new tree, and I'm done. And if I'm deleting something bigger than the root, I do the same thing. I hand them the right subtree, ask them to delete from that, replace my right subtree with a new tree. If I want to delete the 60, I'm stuck. I can't hand a subtree to a friend and say delete. I can't hand the original tree and say delete 60 from this, because that recursion is never going to end. We're just going to keep handing the same problem to other people. So if you want to delete the root of a tree, you actually have to do some work. But otherwise, let's write a delete function. And just like insert, it's going to have to return a struct node star, because the root may change. I'm going to assume the number is actually in the tree. Otherwise, you need to check to see if you run out of nodes, right? So call search first or write some extra code. But for now, I'm just going to assume the number you're trying to delete is in the tree somewhere. So I'm going to do the following. If number, and since I'm assuming the number is in the tree somewhere, the tree can't be null, because a null tree has no nodes. Right, so I don't have to worry about the case where my root's null, because I wouldn't be trying to delete something from a null tree unless I'm a crazy user. So if number is less than the root node's data, I want to delete from the left. So I'm going to change root left to be whatever I get when I say delete from root left, the node containing num. And then I'm just going to return the root that I started with. And then same thing on the right. If my number is bigger than the root data, I'll change the right subtree to be what I get when I call delete on the right subtree to delete num, and I'll return my root. Otherwise, I got to actually do some work. I'm deleting the root because my number is not smaller than the root, it's not bigger than the root, it must be equal to the root. So delete the root. All right, we got some work to do here. So if I just take 60 and I just say free that, right, I've got two problems. One, my root was pointing to 60 and I've just freed that memory, so if I try to use my root in the future, I'll probably get a seg fault. And two, my subtree here and my subtree there have been orphaned. They're not attached to anything. Now for a particular tree, we can always find some answers to the question, how should we delete the root? We can come up with a lot of ways that we could rewrite this tree without the 60 in it. But we're looking for a general algorithm that'll always work.
A general balanced algorithm.
Ideally balanced. We're not going to worry about balance yet. And actually, deleting and remaining balanced is a really nightmarish kind of algorithm. It'll be fun when we get there.
Oh, joy.
Yeah, it's really elegant. But we're just going to be sloppy. We're just going to say, let's just get rid of the 60 and keep a tree, and then let's get out of here. So there's two ways that we can do this that are equally good. We could replace this with some other node in the tree. But we want to do this in a way that doesn't change the tree from being a binary search tree and doesn't lose anything other than the 60 in this case. So the main thing a binary search tree has to have is everything to the left of a node has to be smaller, everything to the right has to be bigger. So if we get rid of the 60 and replace it with something else, we have to replace it with something bigger than everything in the left and smaller than everything in the right. Okay, we're going to pick a number from the left subtree and move it up to the root. And we're going to pick the largest number in the left subtree. So in this case, the largest number is a 30. So we're going to take the 30 and move that up to the root and get rid of the root. And what's this going to do? Oh, I've got a bogus tree. I did this before too. Pretend the 40 is not there. All right. So the largest thing in the left subtree is a 30. So you're going to move the 30 up to the root. Okay, there's two things we can note. One, 30 came from the left subtree of the original tree, which means it's smaller than the root, which means it's smaller than everything over here. So when we put 30 up to the root, everything on the right of the root is going to be bigger than 30. But also, since 30 was the largest thing in this green left subtree, everything in here other than 30 is smaller than 30. So if we move 30 up to the root, everything on the left is going to be smaller. So we're still going to have a good binary search tree. There's an added complication, though, which is when we move 30 up here, 30 is going to adopt this tree on the left, this tree on the right. 30 already had some stuff on the left. And we don't want to lose all of that information. But it turns out, since 30's parent had 30 on the right and 30's going somewhere else, 30's parent can adopt this entire subtree. So after we delete, here's what we're going to have. This is still going to be the same. Our new root's going to be 30. This is still going to be our big line down to 20 and 10. But 20, which lost 30 on the right, is going to adopt 30's child, 25, 23, 22. And you've still got a BST. Yeah?
Could you also replace 30 with one of its children? Or
Effectively, that's what we're doing, is we're just moving this up in place of 30. Yes, exactly. What happens if 30 has something on the right, though?
Then it would have been bigger and would have showed that.
Exactly. If 30 has something on the right, 30 is not the biggest thing in this subtree. So we know 30 has at most one child, and that child can move up in place of 30. Well, what does this look like? So we've got to actually delete the root. So you have to do some work. But we're starting off at a root. And there's some nodes coming off here. And there's some stuff over here. And whatever. And we want to delete the root. Okay, we need to identify the largest thing in the left subtree, and that's going to be this node here. So that's going to be largest. And we can find that pretty easily. We move down to the left subtree and we just go as far to the right as possible. And if you think about left node, right traversal order, the last thing you're going to do is the node that's most to the right. And the last thing you traverse is going to be the largest. So we have to write some code that lets us eventually find what this largest node is. And we also need to know what the previous node is. So as we're moving down to the largest, we're going to do this previous current thing. And when we get down to a spot and we say there's nothing more to the right, okay, that's the largest. The node we were at right before, that's the previous. Okay, what do we do to delete the root? So here's the root. This practically writes itself. Okay, we need to take the left child of largest, and that has to get adopted on the right of previous. And we do that with something like this. Previous right equals largest left. That does this. And then largest left is now available. And we're going to set that equal to whatever the root has on the left. So now this entire subtree is hanging off the left of largest. And then largest right, which we know was already null, we set that equal to root right. So now all of this is hanging off the left of largest, all of this is hanging off the right of largest. And we've pushed the top down of the tree, but if you pull it back up, it looks like a tree suddenly. And we don't need root anymore, so we can free root. And then we return the root of the new tree, which is largest, so we just return largest. So you have to find previous and largest. And then it's just a few statements to manipulate the nodes to perform the deletion. So this may not be crystal clear the first time you see it, or the first few times you see it. The punchline is there's two things here. There's an algorithm, which you hear about or you read about, and then you work out some examples on paper, and you sort of try to internalize what's going on in the algorithm. And then once you figure out what the steps of that algorithm are, you write some code that correspond to each of the steps. And the more you do this, the more the translation from here to this is pretty automatic, right? And then you debug if it doesn't work. But it's actually remarkably comfortable writing things like this once you're not thinking anymore about what these things mean. Right? This becomes synonymous with these arrows in your picture and so on, and that's what's going on in PA1, PA2, and eventually PA4. All right, so we will definitely go through all of this in a lot more detail and with some sample code, and we'll look at some stuff running when we get back next week. So tomorrow is the midterm, and Monday we'll probably talk about the midterm, and then probably Tuesday we'll start back in with continuing with trees.
I think next time we have snow.
Or Monday will be a snow day. And
That's
then
why my physics class is canceled.
physics class, cool. All right, so I will see you tomorrow.